along the x-axis, we can assign a new transformation matrix where the row 4 is not 0, 0, 0, but actually describes an offset relative to the world coordinate system. If we would assign this new matrix to the transform property of the object is moved to the new location. Note that the scaling and the rotation remain the same. The only thing that changed is the translation. If we would like to scale the object relative to the world coordinate system, for example, make it twice as long along the z-axis, we can multiply the third row, for example, with 2, and in this case, the object is both translated to 100, 0, 0 and scaled so that its z-axis is twice as long as the x and y. We can enter 2 for the other axis, and looking at the result in the transform type in, we can see that the x, y, and z transformations are reflected accordingly. So this shows that the first, second, and third row contain scaling information, but they also contain rotation information. That means in the current matrix that we're using, the x, y, and z axis point along the world x, y, and z. If we would rotate the object to 45 degrees about the z-axis and take a look at its transformation matrix at this point, we'll note that the x and y contain familiar values, which are the cosine of 45 degrees and the sine of 45 degrees. Both have the same value. Since this vector now contains the projection of a vector which is pointing at 45 degrees on the x and the y axis of the unit circle that we looked at when we were talking about sine and cosine functions. The same can be said about the y-axis. We see a minus and a plus value, which is the cosine and the sine, basically the projections of this axis on the x and y. And the third axis, the z, hasn't changed because the only rotation that we applied was around the z-axis. The axis itself is still aligned to the world coordinate system. Obviously, we're not going to enter by hand meaningful numbers for scaling and rotation at the same time. We're going to use a higher level functions and operations using matrices and vectors in order to achieve the same results. We don't really have to know what numbers to type in there, but we have to know what those numbers mean when looking at a transformation matrix of a node. The transformation property can be used to acquire information about the translation, rotation, and scale. Actually, any matrix tree value has these read-only properties. We cannot assign to them, but we can read them and access the translation part, the rotation part, as a quaternion rotation, and the scale part, which in this case is 1, 1, 1. Obviously, if the transformation was different, scaled twice along the z, then the scale part would return 1, 1, 2. Trying to assign a value to these properties returns a runtime error because this is not allowed. Similarly, it's important to note that it's not possible to assign directly to a row of a transformation matrix. For example, if we want to change the row 4